Okay, welcome to day two. We're going to work on something called the instantaneous rate of change, but today we're going to change its name to the derivative. So you can see on the top of the page, I'm calling this calculus. We are actually going to do calculus material today. So we remember the average rate of change. We've done this. We've done this many times this year. In the third quarter, I put this on every quiz once we got to that point. And what we've been talking about is the average rate of change between point A and point B, which is basically this line right here, what we call it as a secant line, because it goes through 2 points on a curve. And what we're going to work on now is we have this distance h between the 2 points, and we want to see what happens as h becomes smaller and smaller, or as we squeeze the 2 points together. We get them closer and closer and closer and closer. So what happens is that the average rate of change, which is a secant line, gets closer and closer and closer to the instantaneous rate of change, or we call it a slope of the tangent line. And if you think about what you did in physics class, you drew some lines between points on a distance time curve, and the slope between those 2 points was your velocity. But once in a while you drew a tangent line, and that was your instantaneous velocity. It's pretty much related. So the idea is that what happens if we bring this closer and closer and closer together, and what happens if finally h becomes 0? Well, that means h, if you notice here, we have all these slopes. We have this line here in blue, and then we have this line here in purple, and then one in green. These are all, maybe one in red. All these guys are secant lines. But finally, when A gets on top of B, at the very end here, this last line, right here, I'm going to do pink. This last line right here, this is a tangent line, because what's done is immediately h is equal to 0. And that slope of the tangent line is the slope of the curve at that point A. It's also known as the derivative of this function. This is what we've been working to get to all year. That's find the derivative. Derivative is just a fancy name for a slope, or instantaneous rate of change, or slope of the tangent line, or better yet, we're going to use these notation. These three are just special notation. This one with the f with the tick mark is called f prime, y with the little tick mark is called y prime, and dy over dx. Wow, that looks very familiar. Looks very, very close to dy dx, kind of like delta y over delta x. Sounds like slope to me, and that's what we're working on. So our definition of the derivative is going to be this formula that we've been using all year, the f of x plus h minus f of x over h, except we've added one more step. And this extra step is when we're done, we have this whole limit right here. I'm going to put it in light blue. This limit as h goes to 0, so at the very, very end, we're going to plug in h equals 0, and we're going to get rid of that h. So we're going to do exactly what we've been doing all year, except one more step, plugging in 0 in for h. So here's my formula. So I'm going to say f prime of x equals the limit. Don't forget this limit as h goes to 0. I have this fraction bar, f of x plus h minus f of x over h. And what do I really have? instead of calling f of x plus h is really x plus h squared minus x squared. And I'm going to clean this all up. So you should remember what x plus h squared is. We've done it many, many times. X squared plus 2xh plus h squared. Don't forget that middle term. So now I have equals the limit as h goes to 0. I'm going to put this every single time. X squared plus 2xh plus h squared minus the original function of x squared all over h. And now this is where I cancel in the numerator. Boom and boom. Okay. Only h terms are left. Anything without an h will cancel out. So what's left over equals the limit as h goes to 0, 2xh plus h squared over h. And I can cancel 1h everywhere. 1h, 1h, 1h. And I have right now the limit as h approaches 0 of 2x plus h. And we're used to getting that whole, we're used to getting this 2x plus h as my rate of change. I got one more step, and that's plugging in this h equals 0. Well, that means this goes to 0. So the only thing left over is 2x, and I have to write it in this notation. Notation is going to be counted for, and you better say f prime, or f, the derivative of f of x, is equal to 2x. This is the notation I'm looking for. You do not give me this notation, you will lose points. It is very, very important to write it this way. So the derivative of x squared is equal to 2x. So what does this mean for the graph of f of x? Well, the derivative is a fancy name for slope. So pick any x value you want. I'm going to take right here at x equals 2. And if I do the slope here, well, when I plug it in here, f prime of 2, well, 2 times 2 is equal to 4. That means this slope right here, you see this pink line? This is the tangent line. That slope is 4. If I went over here and use x equals negative 1, well, f prime of negative 1 will be 2 times negative 1, which is negative 2. That slope, you see right here, that this purple line, that slope is negative 2. That's what we're doing. We're figuring out the slope of the curve, and that's what the derivative is. It's the instantaneous slope or rate of change. Let's do one that's a little bit harder. I made you do the rate of change for these all throughout the year, so you should be very used to this, except now we're going to say f prime of x is equal to, don't forget the limit as h goes to 0, of 2 parentheses x plus h squared minus 3x plus h plus 4 minus the original function all over h. And I'm going to clean it up algebraically. Okay, I expanded it out. You're going to get big numerators when you do this. You know you did before. I know my last three guys that don't have h's all have buddies that don't have h's that cancel out. I can rewrite this. And I can cancel out 1h everywhere. So 1h cancels out here, 1h cancels out here. That goes away, that goes away. So you notice in every step I always carry that limit as h goes to 0. And now when I get to the last step, when I don't have that fraction anymore, I don't have the denominator, I can plug in h equals 0. So this term right here that has an h in it, I put an arrow through it, it goes to 0. And I write as my final notation f prime of x is equal to 4x minus 3. That is the derivative of the original function of f of x. And there we go. So let's find the derivative of f of x equals x cubed. So f prime of x is equal to the limit as h goes to 0 of x plus h to the third minus the original function f to the third over h. Now I have to remember, what is x plus h cubed? Well, that's what we did yesterday with Pascal's triangle. Well, the third row is 1, 3, 3, 1. So it's going to be x cubed plus 3x squared h plus 3x h squared plus h to the third. 1, 3, 3, 1 are the coefficients. So I put in my problem, and I can cancel everything in the numerator. It doesn't have an h. Bye-bye, bye-bye. I can rewrite it. And now I can cancel one h in every term. That h goes away. That h goes away. It becomes h to the first. This becomes h to the second. And now that I don't have that fraction any longer, I could plug in my h equals 0. Well, there's an h here that goes to 0. There's an h here that goes to 0. And I finally get f prime of x is equal to 3x squared. And I'm going to tell you something. For these last couple problems, there is a pattern to finding the derivative without going through this whole process. That is tomorrow's lesson. And you're going to be like, wow, this is much easier. But you have to develop the derivative by its definition first. It is key to calculus to know how to do this whole f of x plus h minus f of x over h, and then using the limit as h goes to 0. Okay, much more difficult problem. F prime of x equals the limit as h goes to 0, x plus h cubed, which is going to be messy, minus 5x plus h squared, which has got some stuff to do, plus 4x plus h minus 7, minus the original function, all over h. And now I have to expand everything out, including that x plus h to the third and x plus h squared, and so on and so forth, and multiply things out. It is going to be very messy. So you look at this numerator, there's a whole lot of terms there. I think there's 14 total. It's pretty messy. Well, these four here are 1, 2, 3, 4 don't have h's, and they all have buddies earlier that do not have h's. So now I can rewrite this problem without the terms that don't have h. Now I can cancel out 1h everywhere. 1h, 1h, h to the first, squared, 1h, 1h, 1h. And I can rewrite it as a limit as h goes to 0 of 3x squared plus 3xh plus h squared minus 10x minus 5h plus 4. And then I can plug in my whole h goes to 0. There's an h here, it goes to 0. There's an h here, it goes to 0. There's an h here, it all goes to 0. And when I'm done, I get f prime of x is equal to 3x squared minus 10x plus 4. So that the whole mess that we had in blue got filtered down to something not so bad. So how do I find derivatives at certain values for x? Well, all I have to do is find the general derivative using my definition, and then plug that number of x into that derivative, and I'm going to get f prime at that specific value. So again, I'm going to go through this whole process. I took an easier function than what we just did, and then when I'm done, I'm going to plug in x equals 3. So you see, I plugged in my x plus h for everything, and I'm going to expand it by multiplying everything out. I could cancel all this terms in the numerator that do not have an h in it. I can cancel out 1/8 everywhere, just like we've been doing. Now I could plug in h equals 0, and I do that, and I get f prime of x is equal to 2x plus 5. That is the general derivative for the original function f of x equals x squared plus 5x minus 4. But now I could plug in, when I said use this later, I'm going to use it later. I can find f prime of 3 by plugging 3 in here. I get f prime of 3 is equal to 11. So what does this mean? This is the, I'm going to pick a different color. This is the slope of the tangent line at x equals 3 for this original function f. So one more step we're going to do. We want to find from finding derivatives to finding the slope at a specific point. Now we're going to write the tangent line equation. Well, if I want to write a linear equation, I usually write it this way. I could modify it and do where I have a slope and I need a y value, and sometimes I'm not given a y value, so I plug it in. So what do I need to write? A tangent line equation. I need an x value, which is going to be given to you. So this x value is going to be given to you. I need a y value. So if I don't know the y value, all you have to do is plug the x value into the function itself, and now you have the y value. So you have an x and a y value. The only thing you need left is slope. So how do I find slope? Another word for slope is the derivative. So use your derivative formula to find the derivative. Once you have that derivative, plug that x value into the derivative that you just found, and once you do that, you have the slope. So this equation that we use all the time can be modified where f prime of x1 is the slope that I want, and f of x1, not f prime, is the y value that I want. So let's see how we're going to do this. So I have a function and a given x value. What else do I need? I need a y value. How do I find a y value? Plug 1 into the function, and when I do all that, I get f of 1 is equal to 5. Therefore, I know I have the point 1 comma 5. I'm going to use this later. Step 2, find the derivative. So I take my whole derivative definition I've been using all day, plug in this whole x plus h into the original function, subtract the original function, all over h, and now we can clean it up. I could cancel out terms in the numerator. I could cancel out 1h everywhere like we've been doing. I can set my h equal to 0, and I have f prime of x in general is equal to 6x minus 2. Now this is not exactly what I want, but this is the derivative of the function. Now I could find the derivative at that special point. What point am I using? I'm using the point x equals 1. I plug it into the derivative I just found. I have f prime of 1 is equal to 4. And to me, this is the slope of the tangent line that I need to finish out what I want. I have a point, an x and a y. I have a slope. So step 4, writing the linear equation, y equals m. 4 is my slope. X minus 1 plus 5 is the slope of the linear equation that I wanted to write for the tangent line.